Welcome back to Hansen Theory. So far, you have learned molecular forces, Hansen Space, Ra distance, red number, polymer behavior, solvent blend design, pigment-resin interactions, cross-linking and curing interactions, and predictive troubleshooting. Now, we move into a critical mastery stage, multi-component formulation optimization. This is where coatings engineers integrate all previous knowledge into designing high-performance systems that are robust, scalable, and predictable. Multi-component systems are everywhere in coatings. Clear coats, primers, industrial coatings, and automotive topcoats rarely use a single polymer, pigment, solvent, or additive. Each additional component introduces new interaction vectors. Each change shifts the system in Hansen Space. Minority-thinking engineers optimize these interactions systematically rather than by trial and error. Let's begin with system mapping. Every component, polymer, solvent, pigment, additive, curing agent, has coordinates in Hansen Space. The first step in multi-component optimization is to plot all components in a 3D interaction framework. This allows engineers to visualize clusters of compatible components, critical distances, Ra, that may cause instability, red values that indicate borderline or incompatible interactions. Once mapped, the next step is weighting contributions. Not all components influence the system equally. Solvents are usually volumetrically dominant. Polymers define structural behavior. Pigments and additives often have surface-limited effects, but can create local incompatibility hotspots. By weighting each component's contribution to the overall interaction space, engineers can calculate a composite Ra and red for the formulation. Now, consider component hierarchy. In complex formulations, engineers must prioritize which interactions are most critical. Polymer-solvent compatibility often governs dissolution and swelling. Pigment-polymer interactions dictate dispersion and opacity. Additive-polymer interactions affect rheology, stability, and cure kinetics. Solvent-pigment interactions influence pigment wetting and flocculation. By ranking interactions, engineers target optimization efforts where they yield the greatest performance benefit. Next, iterative adjustment. Optimization is rarely achieved in one step. Minority-thinking engineers adjust ratios, component selection, or additive type in a controlled sequence. Position the primary polymer within its solubility sphere using solvent selection. Adjust pigment or filler interactions using dispersants or co-solvents. Fine-tune curing agents to ensure red won across reactive sites. Evaluate overall system Ra distance and red values under expected process conditions. Repeat until all critical interactions fall within acceptable thresholds. Now, let's address interaction conflicts. Adding one component may improve compatibility in one area but worsen it in another. For example, a co-solvent may improve polymer dissolution but increase Ra distance with pigments. Experienced engineers predict these conflicts using Hansen Space calculations. They select compensatory adjustments to maintain red won across all critical interactions. Next, consider environmental robustness. Temperature, humidity, shear, and evaporation affect multi-component formulations. Minority-thinking engineers simulate these conditions in Hansen Space by evaluating red shifts for each interaction. They design formulations that maintain stability throughout processing, storage, and application. Now, let's discuss optimization metrics. Optimization is not just red won. It includes swelling uniformity for polymers, pigment wetting and dispersion stability, viscosity and rheology targets, cure kinetics and cross-linking density, of film properties such as gloss, hardness, and chemical resistance. Hansen Theory allows engineers to predict these metrics based on molecular interaction balance. This predictive power reduces trial and error iterations, saving time and resources. Next, multi-polymer systems. Complex coatings often contain multiple polymers with different solubility spheres. Optimization requires aligning these spheres with solvents, pigments, and additives simultaneously. Engineers calculate net red for polymer-polymer interactions to prevent phase separation. They adjust solvents or co-solvents to bring all components within a compatible molecular zone. Now, let's address additive synergy and antagonism. Additives are rarely neutral. Some may improve polymer pigment compatibility while disrupting polymer-polymer interactions. Minority-thinking engineers evaluate additive effects holistically. They use Hansen Space to quantify net impact on red and overall formulation stability. Next, consider scalability. Optimization in lab conditions must translate to production scale. Evaporation rates, mixing shear, and thermal gradients alter red values dynamically. Engineers account for these factors during optimization by simulating process conditions in Hansen Space. This ensures formulations remain robust from lab to production floor. Now, a key mindset insight. Formulation optimization is a dynamic system problem. Every change propagates through molecular interactions. Minor adjustments can have amplified effects due to polymer chain entanglement, pigment surface area, and additive concentration. Experienced engineers anticipate these chain reactions and design formulations that are inherently stable. Next, consider troubleshooting during optimization. If a formulation fails, the approach is methodical. Identify which component interactions are outside the solubility sphere. Calculate RA and red values for all critical pairs. Adjust components sequentially to restore red 1. Validate performance metrics under expected conditions. This methodology transforms optimization from guesswork into predictable engineering. Finally, minority-thinking engineers extend this approach to performance tailoring. By adjusting solvents, additives, and polymer ratios, they can modify drying times and leveling, optimize pigment distribution and opacity, control cross-linking density and mechanical properties, maintain environmental compliance, and ensure stability across temperature, humidity, and storage conditions. Multi-component formulation optimization is the pinnacle of applied Hansen theory. It integrates all previous lessons into a structured, predictive framework for real-world coatings engineering. In the next episode, we will explore environmental and temperature effects on solubility and curing, connecting molecular principles to practical challenges in industrial applications. If you want to engineer complex, high-performance coatings with confidence, continue with this series. This is Hansen Theory.